All right, so in 2.3, we're going to be talking about limits in a more algebraic sense. So in the last section, we talked about limits very qualitatively, very visually, but we didn't make things very precise. So 2.3, we're going to transition to, well, how do we do algebra on these things, and what properties can we use to help us in the calculation of limits? So the first 6 properties that you see here are referred to as our limit laws. And they are going to tell us the algebraic properties that we are allowed to use with limits. So suppose that c is a constant and that the limit as x approaches a of f of x and the limit as x approaches a of g of x exist, then it says that the limit as x approaches a of f plus g is equal to calculating the limits independently and then adding them up. So if you have the sum or difference of limits, that's what b is, it says you can just calculate the limits of each of the parts individually and then add or subtract them together. So in other words, the limit of the sums is the sum of the limits, if the limits exist. Similarly, our next property, property c, says that if you have a constant number times a function and you're taking the limit, you can pull constants out of the limit because constants don't change. So all they do is stretch a function by that value, right? That's our vertical stretching or shrinking. So our vertical transformation, so you can pull it out, calculate the limit first, and then multiply by the constant. We can do this to help us simplify the algebra. Similarly, if you have the product of 2 functions and the limits exist, you can then calculate the limits independently and multiply them together. The same holds for division, with the caveat that what's the one thing we're never allowed to divide by? 0. So if the limit of the denominator is 0, you're going to have to do something else. You can't just split them up because you can't calculate the limit of 0 and then divide by it because it doesn't give you a real number. And lastly, we have this one. F is included here. We'll talk more about it later, but it involves function composition. So if you have a function inside a function and the outside function is continuous, you can then pass the limit inside the continuous function and calculate the limit of the inside and then evaluate the function at that point. So we will use all of these properties to aid us in calculating limits. F is pure gold. We are going to love this property, as you will see. It will save you a ton of time in doing things when used properly. So we'll do some examples of all of these. But before we can do this, we need to calculate a couple. Well, let's practice our properties, and then we'll calculate some limits. So example 1, we don't actually have to calculate any limits because our limits are given to us. But we do need to use these properties. So given that the limit as x approaches -4 of f of x equals 5, the limit as x approaches -4 of g of x is 12, and that the limit as x approaches -4 of h of x equals -10, find the limits if they exist. So we want to find the limit as x approaches -4 of -3 times f of x plus 5 times g of x. Well, we look at our properties. So the first property that we're going to want to use is we have the sum of 2 limits. So that means we can break this up. So by a above, this is the same as the limit as x approaches -4 of -3 f of x plus the limit as x approaches -4 of 5 times g of x. Similarly then, we now have a constant times a function. Well, that's property C, so that tells us we can take those constants out of our limit. So that's -3 times the limit as x approaches negative 4 of f of x, plus we pull our 5 out, the limit as x approaches negative 4 of g of x. Well, we know those values, right? So it's negative 3 times, and then the limit as x approaches negative 4 of f of x is 5, plus 5 times the limit as x approaches negative 4 of g is 12. So then that gives us negative 15 plus 60, which gives us positive 45. So that would be the value of our limit. And we got that by using properties A and C from above. All right, so now we look at B. Which properties are we going to want to use in order to calculate the limit as x goes to negative 4 of f times g of x divided by h of x? Well, we have both products, so that's going to be property D, and we have division, which is property E, and the only thing we have to check is the limit as x goes to a of the denominator 0? So what's the limit as h goes to negative 4? Well, it's negative 10, so it's not 0, so we're okay. So then by properties D and E, and we can use them together, we would get the following. We would have the limit as x goes to negative 4 of f of x times the limit as x goes to negative 4 of g of x, all divided by the limit as x goes to negative 4 of h of x. Well, our limit for f of x is 5, our limit for g of x is still 12, and our limit for h of x is negative 10. So let's see, 5 times 12 is still 60. 60 divided by negative 10 is negative 6. So in this case, our limit would be negative 6. So for C, there's actually two different ways we could think about it. Because f of x squared means f of x times f of x. So method 1, it would be the limit as x approaches negative 4 of f of x times the limit as x approaches negative 4 of f of x. And the limit as x approaches negative 4 of f of x is still 5. So then that would be 5 times 5, which is 25. But we'll note method 2, we'll go with z of x equals x squared is continuous. And z evaluated at f of x is going to be f of x quantity squared. So this is actually going to be property f. So by f, we have that our limit is going to equal, we move the limit to the inside, the limit as x approaches negative 4 of f of x goes inside our squaring function, which is just 5 squared, which equals 25. And notice, either way you do it, you're going to get the same thing. But when we have lots and lots of exponents, writing them out, like if you had an exponent of 10, you're not going to want to calculate 5 times 5 times 5 times 5, right? That's just ridiculous. Just pass it to the inside and evaluate the limit, and then raise it to the appropriate exponent. So continuous functions have a lot of nice properties, and we'll see other ones besides exponents where this is going to be helpful. All right, so we were doing this with limits that we were just given, right? Oh, f of x, the limit as x goes to negative 4 of f of x equals 5. Well, let's talk about, well, how do we actually calculate limits? So that leads to the next part of our notes, which is some fundamental limits. So if we visualize our first function here, what is the limit as x approaches a of c if c is any real number? Well, to help us with this, well, what does the graph of y equals c look like? It's a horizontal line with its only output equal to c. So as I approach a, whatever a is from the left or from the right, what is my y value always going to be? C. So the limit as x approaches a of any constant is just going to be that constant. So the limit of a constant is always the constant because the constant doesn't change. All right, so the limit as x approaches pi of 4, well, our constant value is 4, so what does our limit have to be? 4, right? So the limit as x approaches pi of 4 is going to be 4. In fact, the limit as x approaches any number of 4 is going to be 4, right? Because 4 doesn't ever change. So the limit of a constant is always the constant. Our next one is the limit as x approaches a of x. So our function this time is y equals x. And if we graph y equals x, we get a line with slope 1 that contains the origin. So as we approach a from either the right or the left, we know that every point on the graph y is the same as x is going to be the ordered pair a comma a. So as we approach the x value of a, what y value does the graph also have to be getting close to? A, right? So the limit as x approaches a of x is always equal to a. So the limit as x approaches pi of x is going to be what the limit approaches, so we're going to get pi. So the limit as x approaches pi of x gives us pi. Well, now that we know what the limit is for x, we can use all of the properties that we talked about to actually find the limit of any polynomial. So let's do a couple of examples to illustrate that idea. So example 4 says, find the limit as x approaches negative 2 of 3x. Well, our constant property from above was property C, right? So if you have a constant inside of a limit, what do you get to do? You bring the constant out. So then this is the same as 3 times the limit as x approaches negative 2 of x. And this is by C from above. And then we know, well, what's the limit as x approaches negative 2 of x? Well, it's negative 2. So then the limit as x approaches negative 2 of 3x is negative 6. So we pull the constant out, and then we use our property that the limit as x approaches any constant of x is just the constant. All right. right, so then example 5. We're going to do the same thing. This one is by property f because we have a squaring function. So this is the same as the limit as x approaches negative 2 of x squared, because we can move the limit inside the squaring because x is a continuous function. So then our limit is going to be, as x approaches negative 2 of x, is negative 2 squared, which is going to give us positive 4. So note, if you did the limit as x approaches negative 2 of x times the limit as x goes to negative 2 of x, you would get negative 2 and negative 2, which is negative 2 times negative 2, which is still 4, right? So there's more than one way to use these properties, and as long as you don't break any rules, there is going to be more than one way to get from A to B. All right, so let's take a look at example number 6. So now we have the limit as x approaches negative 2 of x squared minus 3x. Well, that's by our first property, well actually our second one because it's subtraction. This is the same as the limit as x approaches negative 2 of x squared minus the limit as x approaches negative 2 of 3x. Well, wait a minute. This is example 4, and this is example 5. So if I have example 4 and example 5, I already know what the answers are. So this is going to be 4 minus a minus 6, so minus a minus is a plus positive. So then we would get 10. So as we saw, we can keep generalizing those rules to do any polynomial, right? So what would our strategy be? We break it down into the individual pieces, calculate the limits, and then add or subtract as needed to calculate those limits. So the idea is, as long as you know the atomic limits, we have rules that allow us to calculate the limits of pretty much anything. All right. So let's take a look at example number 7. So we have the limit as x goes to negative 2 of x over x plus 2. And we really would like to use our limit property e, but it says that g of x, or our denominator, the limit can't be 0. Well, what's the limit as x goes to negative 2 of x plus 2? 0. So we can't directly use that property. So this is equal to 0. The limit is 0. So we can't use property e. So then we have to take our limit from the left and from the right. So we have our limit as x approaches 2 from the left of this. So our limit in the numerator as x goes to negative 2 from the left, this is going to be a negative constant divided by, in the denominator, we're going to get 0. But if we're coming from the left, we're using values smaller than negative 2. So a value smaller than negative 2 plus 2 is going to be a negative. So this is negative 0. So a negative divided by a negative is going to be positive, and a constant divided by 0 is infinity. So our left limit, and this was from the previous section, is positive infinity. And if we calculate our right limit, I'm going to get, well, we're still going to get a negative constant in the numerator. Because we get negative 2. And then if we're approaching negative 2 from the right, we're going to have a positive 0. So that's going to give us a negative divided by a positive is negative infinity. So the left limit is positive infinity. The right limit is negative infinity. Are those two things the same? No. So what do we get? dne, right? So we have to remember we can only use those properties if the conditions are satisfied. If they're not satisfied, we're going to have to do our analysis. With division, if the denominator is 0, it's always going to go down like this. Calculate left, calculate right, see if they're the same. Sometimes it works, sometimes it doesn't, as we will see. All right. Let's go ahead and analyze this. So what we're going to do is use our property D, which lets us break it up into two separate limits. So we get the limit as x approaches negative 2 of x plus 2 times the limit as x approaches negative 2 of x to the 4th plus 4x squared plus 4. So now, each of these two things are our functions. So we have two polynomials. So polynomials are continuous. So this is f of x, and this is g of x. And it says we can just pass the limit inside the function, which means we can just pass it into all of the x's and evaluate. So our limit is going to be negative 2 plus 2 times negative 2 to the 4th plus 4 times negative 2 squared plus 4. So that gives us 0 times negative 2 to the 4th is 4, 8, 16. Negative 2 squared is 4 plus another 16 plus 4. Not that we really need that. 0 times 36, because 0 times anything is 0. So this part that we did right here was property F. And that's why I was talking about that one being pure gold, which says if the function is continuous, you just send the limit all the way to the inside to the x's. And what's the limit as x approaches a of x? It's just the a. And what was our a in this case? Negative 2. So it says we can just put it in as long as it's continuous. That is going to be a very, very powerful property, because essentially what does that tell us? Did we even have to do property D? No, because the product of continuous functions is continuous, so you could have just evaluated from the very first step. So you'll come to recognize when doing your homework, you love continuous functions. They're going to be like your best friend because they behave in very nice ways and everything works the way your heart thinks it should, which means you can just put x's in and see what you get out. All right, let's continue with 2.3. So basically what I just said is the following. So we're going to do an example that would be super duper messy if we didn't make that observation that I was just talking about. So the observation is, and this is our theorem, it's called the evaluation theorem. If f is a continuous function and a is in the domain of f, then the limit as x approaches a of f of x equals f of a. So basically, if a function is continuous, we can bootstrap our way all the way up, that if we know a function is continuous at a, then the limit as x approaches a of f of x has to equal f of a. So that means for continuous functions, we can bypass pretty much all of our limit properties and just evaluate the function at that point. Well, it was like the example we started with, right? X cubed minus 1, as x got close to 2, we got 7 and 7. What's 2 cubed minus 1? 7, which was the value of the limit, because polynomials are continuous functions. So whenever you have a continuous function, you can just put the x value in and get the limit. It says that the limit as x approaches a of f of x is equal to the function evaluated at that point if f is continuous and a is in the domain of f. So we have some examples here. Polynomials have domain all real numbers, so you could just plug it in. Rational functions, as long as the denominator is not 0, like when we did example 7, I want to say earlier, the denominator was 0, so we had to do a further analysis. But if the denominator is not 0, just plug it in. Same is true for radical functions, exponential functions, logarithmic functions, sines, cosines. Same is true for tangent. It's not explicitly on the list as long as it's in the domain. You just plug them in. So this makes evaluating a whole bunch of limits a lot easier. So for example, if you try to use your limit properties to evaluate question number 8, you're going to soon discover that that thing is a giant pain in the butt to do if you're breaking it down by all of those things. But we do know that the product of continuous functions is continuous. The quotient of continuous functions is continuous as long as the denominator doesn't equal to 0. So we have a whole bunch of continuous functions. Exponentials are continuous, cosines continuous, logarithms continuous, the radical function's continuous, and we're adding and dividing them. So this whole thing is a giant continuous function. So then what's our limit going to be? E to the 1 squared plus 1 times the cosine of pi times 1, all divided by the natural logarithm of 1 plus the square root of 1 plus 8. So now we simplify. We're going to get e plus 1 times the cosine of pi is, let's see, that's down at the bottom. It's negative 1. So times negative 1 over the natural logarithm of 1 is 0, plus 1 plus 8 is 9, and the square root of 9 is 3. So we get negative e plus 1 over 3. Well, that makes our life a lot easier, right? Told you you would love continuous functions. Things that are continuous are amazing, and they behave very, very nicely. All right. All right, so to resolve u try 4, since it's continuous, we're just going to evaluate at x equals 3. So that's e to the 2 times 3 squared minus 4 times 3 plus 1. So 3 squared is 9, 9 times 2 is 18, 4 times 3 is 12 plus 1. So 18 minus 12 is 6 plus 1 is 7. So our limit is e to the 7th. All right, so now we're going to exploit a property that was mentioned in the previous section. So formally, we're going to record it here, but it says if two functions f and g are equal everywhere except for at one point, x equals a, then the limit as x approaches a of f of x is equal to the limit as x approaches, that's a typo, a of g of x. So sorry, in my notes, they should both be a. That should not be b. I'll write that a little bit bigger. So make sure you make a correction in your notes. So if we have two functions that are equal everywhere except for at one point, their limits have to be equal at one point. So if we take a look at this rational function, we want to calculate its limit as x goes to 2. So we factor. Our factors of 16 of negative 16 that are going to give us positive 6 are positive 8 and negative 2. And in the denominator, we need factors of 18 that are going to give us negative 11. So that's negative 9 and negative 2. So negative 9 and negative 2. And then we'll notice at negative 2, those two things drop out. And that's where we're actually taking our limit. So now we have the limit as x approaches 2 of x plus 8 all over x minus 9. Well, these two things are equal everywhere except at x equals 2. So x squared plus 6x minus 16 all over x squared minus 11x plus 18 equals x plus 8 over x minus 9 everywhere except x equals 2. So then that tells us that their limits have to be the same, right? So we'll notice in the original, can you just plug in 2? No, because you would be dividing by 0. But in our simplified version here, if I plug 2 in, do I get 0 in the denominator anymore? No. So then that gives me that the limit as x approaches 2 of x squared plus 6x minus 16 all over x squared minus 11x plus 18 would be equal to, using this, 2 plus 8 all over 2 minus 9. So that gives me 10 over negative 7, or negative 10 sevenths. And that would be my limit. So if we can reduce out or create a hole in the graph by reducing that point out, we can use the reduced function to calculate the limit. So this is one of our strategies if we ever have a denominator that is equal to 0. So for example 10, we want to take the limit as t goes to 0, but we notice immediately we can't just plug it in because we have a t squared in the denominator. And 0 squared is going to be 0, and that gives us a problem. So the technique we're going to need to use is some algebra, similar to what we did in example 9. We were able to factor and reduce out our division by 0. Well, in this case, since we have a radical, we're going to use the conjugate. So we will use the conjugate of the square root of t squared plus 4 minus 2, and its conjugate. Remember, to find the conjugate of a binomial, you always change the sign on the second part. So its conjugate would be the square root of t squared plus 4, but instead of minus 2, we change the sign to a positive 2. So then the idea is we will multiply the numerator and denominator by the conjugate. So we have t squared plus 4 minus 2 all over t squared times the square root of t squared plus 4 plus 2 all over the square root of t squared plus 4 plus 2. And now if we distribute this out, the square root of t squared plus 4 times the square root of t squared plus 4 gives us t squared plus 4. And the square root of t squared plus 4 times 2 gives us 2 times the square root of t squared plus 4. And if we distribute in our second term now, we get the negative 2 times the square root of t squared plus 4. So negative 2 times the square root of t squared plus 4. And negative 2 times negative 2 is negative 4. And something very interesting happens. And this happens 100% of the time when you multiply a binomial by its conjugate. The middle terms will always be equal but opposite and add to 0. So when we did that foiling, we had the terms in the middle were the same sign, or the opposite sign, but equal. So when we add them up, we get 0. So that gives you a little bit of a shortcut if you want to use it. It's the first term squared minus the second term squared, right? Because the middle two cross terms will always cancel out. And this is basically the difference of squares formula backwards. If you think of it, it's x minus a times x plus a is equal to x squared minus a squared. So that's really what the conjugate is the difference of squares formula being used in the reverse direction. Then we bring that down here. So our simplified version is going to be t squared plus 4 minus 4. So those also add to 0. That won't always happen, though. So then our numerator reduced to just t squared. So we take the limit as t goes to 0 of t squared over, leaving the denominator factored, the square root of t squared plus 4 plus 2. So now in this problem, we have a t squared in the numerator and a t squared in the denominator, so they reduce out. And in our new reduced function, they're equal everywhere except for what value? At t equals to 0. So we accomplished the same thing we did in example 9. We were able to reduce the t squared out of the denominator. So now we can evaluate the limit by using the evaluation theorem. We plug in the value, and we get 1 over the square root of 0 squared plus 4 plus 2. So 0 squared plus 4 is 4. The square root of 4 is 2. And we get 1 over 2 plus 2 is equal to 1/4. And that will be the limit as t goes to 0 of the square root of t squared plus 4 minus 2 all over t squared. So notice, we found the limit is 1/4. We essentially found the value of this function as we get as close as you want to dividing by 0. That's kind of an interesting way to think about something. All right. The next one we want to look at is involving absolute values. And we need to remind ourselves of one of the definitions of absolute value. Most of us think of absolute values in terms of, we know if it's negative, it becomes positive. We can visualize this in two other ways which will be helpful in calculus. One is as a piecewise function, which is it's equal to negative x if x is less than 0 and x if x is positive, or the absolute value of x is equal to the square root of x squared. Because if you square something like negative 2 times negative 2 would give you positive 4, and the square root of 4 is 2. So that's also another way to calculate an absolute value. The reason that this is going to be helpful will show up in the next example. We'll use the piecewise definition of the function to help us. So we want to take the limit as x approaches 2 of the absolute value of negative x minus 2 all over x minus 2. Okay. So then we're going to need to calculate our limit from the left and from the right. So if we take the limit as x approaches 2 from the left, well, if we're approaching 2 from the left, is x minus 2, we're going to need to make our piecewise function for this. Well, x minus 2 shifts everything to the right 2 units. So we're going to end up with the negative of x minus 2, and this is if x is less than 2, and we're going to have x minus 2, and this one is going to be if x is greater than or equal to 2. So we did the composition with our piecewise function, remembering to shift everything 2 units to the right, including our domains, right? So now, when x is approaching 2 from the left, which branch are we going to be in? Well, if we're approaching from the left, that means we're going to be less than 2. So our numerator is going to be negative, oops, not with a highlighter, is going to be negative x minus 2 over our denominator didn't change, x minus 2. So we get the limit as x approaches 2 from the left. These are equal but opposite, so we get negative 1. And the limit of a constant is just the constant. So our left limit is going to be negative 1. And if we rinse and repeat from the right, we're going to be using our other branch over here where it's positive because we're approaching from the right, so we're going to have just x minus 2. So we have x minus 2 over x minus 2, which gives us just 1 this time. So our limit is 1. So then what would our limit be as x approaches 2? Well, our left limit's negative 1, and our right limit's positive 1. Are they the same? No, so what do we get? dne, right? So in this case, our limit does not exist because the left limit and the right limit are not equal. All right. Completes our penultimate example. So here we go for the grand finale. Before we can do this, we need a theorem. So our theorem says the following. It's called the squeeze theorem. If f of x is less than or equal to g of x, who is less than or equal to h of x, when x is near a but x does not equal a, and the limits of f, g, and h exist at a, and the limit as x approaches a of f of x equals the limit of, as x approaches a of h of x equals L, then the limit as x approaches a of g of x also has to equal to L. So basically the idea is if you have these three functions, so imagine you have, here's f, and you have h is down here, does something like this, and g is somehow trapped in between these functions everywhere. Well, what's going to happen to the limits? If you know the limit of f and you know the limit of h, where does g have to be? It's being squeezed in between. That's why this is called the squeeze theorem. So it's telling us if you can trap some function in between two other functions and calculate their limits, you can indirectly calculate the limit of a third function. Hence the squeeze theorem. Some people call it the sandwich theorem. Think of f and h as the two pieces of bread. What's stuck between the two pieces of bread? Everything in the sandwich. So that's what's happening. If you can squeeze it together, it will allow you to calculate limits of functions that we would be unable to do so otherwise. So let's go ahead and take a look at our last example. So we want to calculate the limit as x goes to 0 of x times sine of 1 over x. Well, 1 over x I can't put 0 in because that's undefined. So I don't know how to calculate this limit. But I can make an observation. So the first thing we want to note is the following. That the sine of 1 over x is always less than or equal to positive 1 and greater than or equal to negative 1, right? The sine function is never bigger than 1 and it's never smaller than negative 1, right? So if we multiply the inequality by x, we get the following. Negative x is less than or equal to x times the sine of 1 over x, which is less than or equal to x. Well, this function that we have right here is exactly the function we're trying to calculate the limit of, right? So that is going to be our g of x, right? Because g is trapped in between two functions. And what are the two functions g is trapped in between? Well, g is bigger than negative x, so that's our f of x, and g is greater than, or g is less than positive x and greater than negative x. I said that backwards. So now, by the squeeze theorem, we can calculate the limit as x goes to 0 of all three of these things. So what's the limit as x goes to 0 of negative x? Well, that's going to be 0 is less than or equal to the limit as x goes to 0 of x times the sine of 1 over x, which is less than or equal to the limit as x goes to 0 of x. Well, that's just going to be 0. So these two things are the same. So by the squeeze theorem, if the limit has to be less than or equal to 0, but also greater than or equal to 0, what's the only choice for the value of that limit? 0. So the limit as x goes to 0 of x times the sine of 1 over x is equal to 0 by the squeeze theorem.